Hello class, we're going to talk about section 1.1 today. Chapter 1 is all about reasoning your way through problems and how to problem solve. So we're going to start with inductive and deductive reasoning with this section. Hopefully you all watched the movie clip already. If you haven't, stop this video and watch the movie clip of the 1995 movie Die Hard with a Vengeance. That movie was really cool. It had a lot of different riddles and problems to solve, where Bruce Willis, which played the character John, and Zeus, who is Samuel Jackson, were running all over town to try to solve the problems and then try to catch up with the villain, whose name was Simon Gruber in the movie. So Simon plants a bunch of bombs around the city, poses a bunch of riddles and puzzles, and then John and Zeus have to disarm them. In one situation, Simon gives them the following riddle to disarm a bomb at a fountain in a park. So hopefully you watched the video. Again, if you didn't, watch it and then come back to this video. So Simon tells them in the video, on the fountain, there should be 2 jugs, a 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water, place it on the scale, and the timer will stop. You must be precise. 1 ounce, more or less, will result in detonation. If you're still alive in 5 minutes, we'll speak. Now, did John and Zeus survive? Well, of course, it's a movie. They're not going to kill them off. But can you solve the problem that was presented before them? Now, there's a couple ways of doing the problem and solving this. One way was done in the movie. They didn't really show you in that movie clip exactly how they did it, but they ended up with some sort of negative space and they filled it up and got 4 gallons. The other way that you can do it is more on the positive space of actually measuring out 4 gallons. Now, there is some YouTube videos that kind of do a graphic of how to do this, and I will post one of those for you to see as well, just so you can see the graphic of it. But in the meantime, here's the description. So this is one way of doing it. With both jugs empty, fill the 3-gallon jug full and pour it into the 5-gallon jug. Now, then fill up the 3-gallon jug again and pour it into the 5-gallon jug. So what happens is, when you have 3 gallons and you pour it in, it's empty. But when you have 3 gallons and you pour it in again, then that only leaves 2 gallons that you can fill up in the 5-gallon jug because it already has 3 gallons in it. That leaves 1 gallon left in the water jug of the 3-gallon jug. So if I have 3 plus 3 minus 5, I filled it up, but I can only pour out 5 gallons. That leaves 1 gallon in the 3-gallon jug. Now, let's start all over. Empty the 5-gallon jug. You're left with 1 gallon in the 3-gallon jug, and that's what you need. Pour that 1 gallon into the 3-gallon jug. You have 1 gallon. From the 3-gallon jug, you have 1 gallon in the 5-gallon jug. Then go back and fill up 3 gallons again. Pour it in there. That results in the 1 gallon that you poured in there, plus the 3, and that equals exactly 4. The other way you could do it would be the opposite way, which is kind of like going from the 5-gallon to the 3-gallon and then back to the 5-gallon. Okay, a little fun on the movie there. There are more riddles in the movie. If you haven't seen the movie, very good movie. You should watch it. So a little math history here. Math can be traced back as far as 3000 BC to Egypt and Babylonia. They developed math to help them solve problems. When they solved problems repeatedly, they formed what they called a recipe. So similar to like when we have a recipe to cook a cake, it works every time. So that's what they were thinking. A recipe is something that works repeatedly and works every time. If the method worked for one problem, then they concluded it would work for a similar one. Now, if it keeps working for other problems, then they can make a conjecture, and that conjecture tells them this recipe works. So specifically, what is a conjecture when we're referring to math? Now, you'll hear the word conjecture in legal and law stuff as well. But in math, a conjecture is going to be an educated guess based on repeated observations. So, like I said before, if a recipe works again and again and again, then we can draw a conclusion or conjecture. We can make an educated guess based on this repeated observation that our recipe works. Now, when we make an educated guess based on repeated observations, this is also called inductive reasoning. So a more formal, I guess, definition of inductive reasoning is going to be the conclusions that you might make using repeated observations So inductive reasoning officially is going to be the conclusions that you draw using repeated observations. Now, the conclusion, or we can call it the conjecture, may or may not be true. Now, again, this is just based on repeated observations. So what you are seeing, you might think works all the time, and you kind of make a conclusion that, hey, this works. So you draw a conclusion just based on sheer observations or repeated patterns. Now, you can test these conjectures or conclusions or educated guesses by finding what is called a counterexample. And a counterexample means that all you've got to do is find one example, just one time, that proves that your educated guess was false. So you might think it's true, but if I can find one example that says you're not true, then that's called a counterexample, which means even based on your observations, your conclusion is not true. So when we find a counterexample, we're trying to prove something is not true. And if we cannot find a counterexample, then chances are that our conjecture and everything is true. So we're trying to prove it. Let's look at page 2. As time progressed, Greeks did not accept conjectures as the absolute truth. Again, they didn't just assume just because you said it was true, it's true. So they proved it, or proved the conclusions, by using what's called deductive reasonings. This is when concepts were applied to problems, and this results in more structure and rules and the actual logical development of mathematics. So deductive reasoning is whenever we apply general rules to specific problems. Now, reasoning through a problem usually requires what we call certain premises. So a premise can be an assumption or a law or a rule or anything similar to that is believed to be true. Then your logical conclusions will follow. So if something has already been proven or proven to be true, or it's a statement that everyone in the world believes it's true, that's called a premise. So let's kind of look at the little flowcharts of how this reasoning works. So when we're talking about deductive reasoning, that's the one right up above here. So this is going to go from something more general to more specific. Deductive reasoning uses facts, definitions, accepted properties, premises would be among those, and then we use all of these to draw a conclusion, and then we have our logical argument or our conclusion. Inductive reasoning works from more specific observations to broader generalizations. So we're looking at something very specific so that we can generalize for larger things. Deductive is going to start with more general and get down to a specific proof. So inductive, we're looking at patterns, repeated observations, does this happen all the time, and then we simply draw a conclusion from that pattern. We can verify this or modify this or find a counterexample. So that's after we draw our conclusion, we can try to prove it or disprove it. So let's look at some examples and determine if they are inductive or deductive reasoning and why it is one or the other. So inductive or deductive. Okay, number 1. It has rained every day for the past 6 days, and it is raining today as well. So it will rain again tomorrow. Now, how did you come up with that conclusion that it's going to rain again tomorrow? Well, this is a pattern. It's rained every day. You've sat there and watched it. It's rained every day. So this is a pattern of observing rain. So you just kind of draw a conclusion. Well, if it's rained for 6 days, it's probably going to rain for 7. And that pattern is how you use inductive reasoning in order to come up with that conclusion. Alright, number 2. Carrie's first 3 children were boys. If she has another baby, it will be a boy. So you've come to the conclusion that she's going to have another boy based on your observation that, well, her first 3 kids were also boys. So again, this is another pattern, another observation. And this is a pattern of Carrie having a bunch of boys. Does that mean she'll have a boy? That means your conjecture may or may not be true, but you are drawing a conclusion based on what you have already seen and what you know. So this is inductive reasoning. Finley has 85 baseball cards. His mom gave him 20 more. Finley now has 105 cards. So how did you come up with the conclusion of 105 cards? Well, that is not a pattern, it's a rule. And what kind of rule did you use? Well, basic math. The math would be addition. So we just took 85 plus 20, and that gives me 105 cards. So the rule of addition is a rule, so that means this is deductive reasoning. Alright, let's continue looking at some more examples. Flip over to page 3. Number 4. Doctors earn a lot of money. I want to earn a lot of money. I should become a doctor. Well, how do you come up with the conclusion that you should be a doctor? And that conclusion is based on something that most everybody knows and everybody accepts as a fact or true. That doctors earn a lot of money. So this is a premise. A premise that doctors make money. Your conclusion is based on a fact that is believed to be true. So a premise that doctors make money. Now, when you use a premise to make a decision, then that is deductive reasoning. Based on something that you believe or everyone else believes is true, that is a premise. Doctors make a lot of money. I should be a doctor if I want to make a bunch of money. Alright, what are the next 2 terms in the sequence? Well, what we're looking at is a bunch of numbers, and we need to figure out how they're going from one number to the next, and then that will let us know how to get to this number and then the next number, and we could continue this. This is a pattern. So because this is a pattern, then this is inductive reasoning. You're going to use a pattern to come up with your solutions. Now, what would that pattern be? what do I do to go from 5 to 9, 9 to 13, 13 to 17 to 21, 25, 29, and what would I do to get to the next number? Well, if you figured out the pattern, you're just simply adding 4 to get to the next number. So 29 plus 4 is 33. 33 plus 4, 37. So a simple pattern when you're looking at number patterns is also inductive reasoning. It's a pattern. Doesn't matter if your pattern is something you observe, something in science, or if it's numbers. A pattern is inductive reasoning. What are the next two terms in the following sequence? So again, this is a number pattern. And since we are using a number pattern, then this is inductive reasoning again. So going from 2 to 4, 4 to 8, 8 to 16, 16 to 32, what kind of pattern do you do to go from one number to the next? Well, this is going to be multiplication. So we're going to times our numbers by 2. So 2 times 2 is 4, 4 times 2 is 8. So 32 times 2 is 64, and then 64 times 2 is 128. So these numbers could keep going on and on and on. All right, number 7. What are the next two terms in this sequence? So again, we have another number pattern. So this is another pattern. So again, we are using inductive reasoning. And I'm going to pause for a really long, awkward time to give you a moment to figure out what this pattern is. So I guess you can fast forward it if you really want to. Pause it to see if you can figure it out on your own. Let's see what you think. Maybe I'll hum the Jeopardy theme song. We're starting out with 1. And then we go with 1 again. But then the next one is 2. So how do I go from 1 to 1, which didn't change, then from 1 to 2, which did change, and then they continue to change from that point on. 2 to 3, 3 to 5, 5 to 8. Now notice these don't change. If I add 1 to it, I get 2. If I add 1, I get 3. But the problem is adding 1 doesn't continue. This is adding 2. This is adding 3. This is not adding 4. But if you think of what you're adding, what are you adding to get to the next number? This is adding 5. This is adding 8. Notice those numbers are here. So what you're doing is, this is actually called the Fibonacci number or Fibonacci sequence, named after a mathematician, Fibonacci. Fibonacci has figured out a lot of patterns in nature and math, and this is one of them. So the pattern is that you add the previous two terms. So if I start with 1, there's not anything in front of 1, so 1 plus 0 is just 1. Then if I start with 1, I add the first 2, so 1 plus 1 is 2. Start with 2, 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34. Then I take 34 plus 21, and I get 55. Then you would take 55 plus 34, and you would continue that pattern. Fibonacci, famous sequence. Fibonacci sequences show up in a lot of things that deal with mathematics. Right, number 8, how do you solve this problem? So how would you solve this problem? Here's A is 3, B is 4, so I need to know C. Now this triangle is a unique triangle because it is considered a right triangle because that is a 90-degree angle. Do you know somehow, some way that you can, what you can do in order to figure out what C is? Well, if we're doing math like this, that means we're going to apply rules. Anytime we apply rules, this is going to be deductive. Deductive reasoning. Now, the rule that we're going to apply here is the Pythagorean theorem. And the Pythagorean theorem states that there's a formula that if you square A and square B, then that would equal C. That is also squared. So Pythagorean theorem is A squared plus B squared equals C squared. So if A is 3, 3 squared plus B squared is 4 squared, and that tells me what C squared is. So 3 squared is 9 plus 16 equals C squared. Well, 9 plus 16 is 25. So 25 is C squared. Now that means this is a square number. What number do you square to get 25? And that tells me what my C is. So that would be 5. Pythagorean theorem. Alright, the last little bit of information is just kind of another number pattern. So this is really just going to be using inductive reasoning, but this is kind of cool the way this works. So legend has it that there was a mathematician, which there was, Carl Friedrich Gauss is his name, at a very young age, was told by his teacher to find the sum of the first 100 counting numbers. So counting numbers, if you think about where you start counting at the very lowest, you start counting at 1. So starting with 1, and you count all the way up to 100. Carl simply wrote down a single number and handed the correct answer to his teacher. The young Carl explained that he observed that there were 50 pairs of numbers that each added up to 101. So the sum of all of those can be done quicker by doing multiplication. 50 pairs times what they total, which is 101, and that equals 5,050. So let's take a look at what he saw. Number 1, number 2, number 3, 98, 99. So we're going to match these up. There's 100 numbers. So if we match up each one of these with 2 numbers, that means we're going to have 50 pairs, which basically you can think of it like half of 100. So if I take 1 and 100, then I'm going to add up to get 101. 100 plus 1 is 101. Alright, let's look at 2 plus 99. Well, if I add 2 plus 99, I still get 101. 3 plus 98. If I add those together, I still get 101. And if we keep doing this, 497, 596, if we keep adding those like that, we're going to come up with 50 of these different little rings that add up to 101. So what's quicker than doing a bunch of adding? Well, multiplication. So if I do these rings, I'm going to get 50 of those because that's half of 100, and we're putting 2 of them together. So 50 of these pairs, and each one is going to equal 101, so we multiply because that's quicker than addition. 50 times 101 is 5,050. Pretty cool. Inductive reasoning. Alright, let's look at page 4. Let's do a few examples of these. Okay, let's look at number 1. If we're looking at number 1, this is very similar. We're just going to add up what 1 plus 2 plus 3 and continue all the way through 400. So let's see what we know the pattern is. So the pattern means we're going to put 2 of these numbers together. So if we do them by 2s, that means we're going to have half of that number. So half of 400 would be 200. but I need to see what these pairs are going to add up to be. So let's start here. 401. So 400 plus 1 is 401. If we move on to the next one, we would do 399 plus 2 is also 401. If we do 398 plus 3, then again, 401. So 401 is our sum, or when we do the addition. So how many pairs, how many times could we make these loops matching up pairs? Well, you would come up with half of this. So half of 400 would be 200 pairs of numbers times what they total when you add them together, which is 401. And then 200 times 401 is 80,200. Whole lot quicker than sitting there and punching in your calculator 1 plus 2 plus 3 plus 4 plus 5 all the way to 400. Alright, let's look at number 2. Okay, number 2 is very similar. So we're going to look at adding up numbers all the way up to 1,000. So again, we're going to see what our sum is right here. So 1,000 plus 1 is 1,001. So 1,000 plus 1 is 1,001. That means 999 plus 2 is 1,001. And then 998 plus 3 is also 1,001. So that is our sum. If we kept drawing these circles and matching up two numbers, we would end up with 500 of these little circles. So that means we would have 500 pairs, half of 1,000. So 500 pairs of numbers that when you add them together, they will equal 1,001. So we'll multiply 500 times 1,001, and we end up with 500,500. Cool, huh? Now, notice that the two examples and the examples on the previous page all had even numbers. So number 3, we're going to do a little bit different because we're wanting to add up to equal an odd number. So 1 plus 2 plus 3 continued all the way up to 175. Now, if it was 174 or 176, we could continue doing what we're doing. But with an odd number, that means that whenever I create all of my pairs, then I'm going to have a number that's left out. So the easiest thing to do is go ahead and leave out the 1. So think of like dividing 175 by 2. So if I would divide, we'll do old school. So if I say 2 divided into 175, so 2 times 8, 16, 1 times 5, so 87, it's 14, and I have this one remainder left over. So that one remainder left over just means I've got just an extra number 1. So I'm going to take this extra number 1 and I'm just going to keep it here. I'm not going to connect 1 plus 175. So I'm just going to kind of keep it over here. We'll add it back later, but just not right now. So let me erase this. Now I'm going to add that 1 back later. Now if you look at the textbook, there's like a quick little pattern you can do this. It has to do with a lot of fractions though. You would say 175 divided by 2, so you would get like 87.5, and then times it times your sum, and that's actually pretty quick and pretty easy. That is probably something you might work with. You can also do different modifications of the Gauss method by adding up even numbers and odd numbers and a bunch of patterns. We're going to keep it pretty simple. We're just going to simply add up to an even or an odd number here. Just basically introducing this pattern to you. Okay, so let's look at, now, let's start with 2 plus 175. And that's going to be 177. So I take 175 plus 2, that's 177. 174 plus 3, that's also 177. 173 plus 4, 177. So 177 is going to be my sum. Now remember what I said earlier, if we are dividing this in half, we get 87 pairs plus that one. So if we do 175 and we're going to subtract that 1 right there, we end up with 174. So 174 divided by 2 gives me my 87 pairs, because that's an even number. So if we take out the 1, that 1 is what makes it odd. So we end up with an even number, 174. So I have 87 pairs that are going to add up to 177. So 87 pairs of numbers times my 177 equals 15,399. But don't forget, we set out the 1 and said we would come back and add it later. So now I'm going to add my 1 here. And now the sum is 15,400. So again, it is still the same idea. You're basically dividing everything in half, just like we did up here. It's just that since this is an odd number, you have that little remainder of 1 left over. So let's just hold off and not start with the 1 like we did up here. We'll just add this 1 back later, start with the 2, figure out those sums. So 2 plus 175, 3 plus 174, like we did over here. 177 is that summation. And if I take the 1 out, that leaves me with 174. That leaves me with 87 pairs, because this is odd. Taking out the 1 leaves me with a nice even number. Then I can divide it in half, just like half of 1,000 is 500, half of 400 is 200. So then you go back and do what you've been doing, 87 pairs of numbers that add up to get 177. Then go back and add the 1, and you have 15,400. Pretty cool. So how did you modify to get this sum? Well, 175 is odd. So if I divide, I can't spell apparently. So if I divide by 2, then I have 1 left over. In other words, that 1, if I take it away, it's going to give me an even number, and that's all that I need. That 1, I'll go back and add it in later. And you're done. Alright, homework is open. Work on homework. If you have any questions, let me know. Otherwise, do good.